Welcome back. This is another video lecture lecture 9.4, and the topic of discussion, one of the most important ideas in all of physics. It's Chapter 9, Section 5, and it's our second conservation law. We're going to be talking about situations in which linear momentum is conserved. So conservation of linear momentum. Remember, in physics, when we say a quantity is conserved, that means its value is constant. So we're talking about a situation, apparently, when a chosen system's linear momentum is constant, does not change. Okay, let's build up that idea, since it is so important. Let's take it carefully and slowly. Okay, I'm going to start with Newton's second law. I'm going to express it for a system of particles, okay, specifically for the motion of the center of mass. So Newton's second law for the motion of the center of mass, when I have a system of particles, n of them, and the total mass of them all together is denoted capital M. All right, we learned earlier in this chapter how to find out what the motion of the center of mass of a system will be. We'll find it's the acceleration of the center of mass using this form of Newton's second law right here. Take the net external force and equate that to the total mass times the acceleration of the center of mass. That's Newton's second law for the motion of the center of mass. Now, if you read section 5 in the book, they will explain to you how it is that the following equality also is true. F net external is also equal to the rate of change of, look at the symbol here, capital P arrow. Capital P arrow is the total linear momentum of the system, right there. Capital P arrow is the sum of the linear momentum of all of the individual particles. You got n particles. You take the mass of each particle times the velocity vector of each particle. You get the linear momentum of that particle. You add up all n of those linear momentum vectors, and you get the total linear momentum of the whole system, capital P. And it turns out the rate of change of that total linear momentum, capital P, is determined by the net external force. Okay? Bottom line, if you have a net external force on a system, really important, external, then the total linear momentum of that system is going to change. By the way, here's a nice little thing to remember about calculating the total linear momentum. Technically, it means do this operation right there. Add up the linear momentum vector for each of the n particles, and that's vector addition, and what a pain that is. But there's a shortcut. You can instead go right to this equality, and it's usually going to be much easier. The total linear momentum is given by the total mass, capital M, of all n particles, times the velocity of that special point called the center of mass. That's just a useful thing to remember. But the bottom line right here is the equation with a star. If you have a net external force on the system, the total linear momentum of that system will change, and the net external force is given by or equal to the rate of change of that total linear momentum. Okay, now, here comes an application of that key idea. What if we have a situation where the net external force on the system equals 0? I am saying specifically F net external vector, net. Add up all the external forces, and when you do that, you get 0. Yes, 0 is a vector, can be a vector. Then what happens? Go back to equation star. Put a 0 in where the F net external is. Okay? What do you conclude from equation star if f net external equals 0? Well, then equation star requires that dp dt must equal 0. Yes? But wait, if the time derivative of any quantity is 0, then that quantity is constant. And that's what conservation means, right? We would say in a situation like this that the total linear momentum of the system is conserved. So here's the tip, kind of takeaway, or one of the takeaways from the material on this slide. The first key step in the application of this new conservation law, right? We have a new one, new conservation law, is recognizing when the condition, net external force equals 0, for conservation of linear momentum for a system is met. All right, so one, you got to know what the condition is. So if we're in our class and I ask the class, hey, when is the linear momentum of a system conserved? I'm asking you about this condition. What has to be true before you know that the linear momentum of a system will be conserved, constant, not changing? And the answer is the net external force on the system must equal 0. You have to be able to recognize when that's true. Because if it's not true, then the linear momentum is going to change. And if you assume it's not changing, you're in trouble. Okay? So you've got to be able to recognize when, once a system is chosen, this condition is satisfied. Net external force equals 0. And that's where we often get into a lot of trouble, is sometimes we assume a system's linear momentum is conserved when it isn't. Or we don't recognize that the linear momentum of a system is conserved, and we can use that fact. So the first real key step in using this idea correctly is knowing when it's true, when it's valid. But there's even more subtlety than that, I'm afraid. This is the world we live in, the universe we live in. That equation star up there is a vector equation. Of course it is. See the arrows? So what I really ought to do, if I go back up to equation star, let me rewrite it down here at the bottom in component form. So equation star by components. So what we really ought to say is F net external x component equals rate of change of x component of total linear momentum. And F net external y component equals rate of change of y component of total linear momentum. And of course z too, but you get the idea. It needs to be applied, equation star, by components. That's always how we deal with vectors in this class. And so, remember the condition for conservation of linear momentum? The net external force must equal 0. That condition, that test, has to be applied by components. And it is indeed quite possible that you could have a system for which, as an example, the net external x force is equal to 0, but the net external y force is not equal to 0. If that is the situation, then for that system, since F net external x component equals 0, dpx dt equals 0, you may use the fact that p sub x must equal a constant, but p sub y will be changing with time. Okay? So you can have a scenario where one component of linear momentum is constant and another component of linear momentum is changing. And we have to be able to recognize a situation like that. Let's get right into practicing with this. We're going to do a lot of practicing. Okay? Practice conservation of linear momentum. And this really is just very basic warm-up practice, not really delving into it in a great detail. That will be when we do Wiley Plus problems, example problems, it's in class, and then you do them as homework. But let's just get started with a kind of a warm-up. Here's a scenario. Suppose we have an object, an orange, that we've released near Earth's surface. An orange. Take an orange in your hand and let go. Near the ground. We all know what we will observe. How many times have we seen things like that happen? Okay, so that's all that's all I'm talking about. Falling orange. Let's choose a system. That's always got to be clarified. What are you choosing as the system? Let's choose the system to be the and only the orange. Question. Is the total linear momentum of that system equal to a constant? Is it conserved? I'd like you to think about that question, pause the video, think about it carefully, form an answer, and then we will discuss. Okay, so I'll call this part 1, system orange, falling near Earth. Okay? There's our surface. There's the orange. That's the closest I can get to orange in color. I'm letting it fall. Okay? There's the system, that thing. Let's even go ahead and take a y-axis here, going like that, so that we know we're going to focus on y components here. Is the y momentum of this system equal to a constant? That's another way to ask, is the y momentum of that system conserved? What's the condition? That's what you should ask yourself. What's the condition for y momentum to be conserved? F net external y component must equal 0. So ask yourself, is that true? Is F net external y component equal to 0 for that system of the orange? Well, I'm pretty sure the answer is no. Why? Because there is an external force in the y direction on the orange, F grav. And why is it external? Because Earth is not part of the system. So a force from Earth is an external force. And so the answer to the question, is P sub y equal to a constant? No. P sub y in this case would be m times v sub y, where m is the mass of the orange and v sub y is its y velocity. But we know that v sub y increases, well, in magnitude, right? When an object's in free fall. So P sub y is increasing too. It's definitely not constant. Okay, that's all I wanted to practice on identifying if linear momentum is conserved in a situation or not. Now let's take a slight change to that. Again, the orange is released near Earth, falling orange near Earth's surface. But now let's take the system to be the orange plus the Earth. For that system, is the total linear momentum equal to a constant? Is it conserved? Pause, think, form an answer, and then come back. Okay, now, I should say, by the way, I should say that I'm going to assume that there's nothing else outside the combo of Earth plus orange that's influencing. And I should have made that clear, so that probably wasn't fair. If I say ignore any external influences outside of Earth plus orange, what would your answer be? The answer is then the linear momentum is conserved. Let's talk about that. And I know that that's not exactly what's going on. We have sun exerting a gravitational force, but I'm just trying to make a point here. So there's the orange. Now I'm just going to actually draw. Now, obviously, this isn't to scale. The whole Earth. Let's say the orange has a mass little m, and then let's say the Earth has a mass big M. That certainly seems an appropriate symbol. And let's again take our plus y-axis, say like that. And we're kind of floating out in space, seeing this. And we're ignoring any other influences from beyond these two. Then the gravitational force on the orange from the Earth is internal, isn't it? Is there a gravitational force on Earth from the orange? Yes, there is. Newton's third law. If the Earth pulls down on the orange, then the orange pulls up on the Earth equally hard. Third law. People don't like that at first, but that's what the third law says. But it doesn't matter. Those gravitational forces, they're internal. The condition for conservation of linear momentum is that there can't be any net external force, right? I don't care about internal forces. Internal forces can't change a system's linear momentum. So now I'm asking, is P sub y equal to a constant for this new system? Your first thought should be, well, is F net external y component equal to 0 or not? And once I clarified that ignore any external influences, I think it's pretty clear that the answer is yes here. F net external y component is 0. There aren't any external forces from anything, so P sub y is constant. So the y momentum of this system can't change. That's a constraint. Let's see what that means. That means the y momentum of the system initial must equal the y momentum of the system final. Notice capital P is for the momentum of a system. And initial and final are 2 points, 2 moments in time that we pick. I'm going to take the initial moment in time to be just as I release them. I release the orange. Just as I release the orange by whatever mechanism I have for doing that. Just then, velocity is 0. And since momentum is mass times velocity, the initial momentum is 0. I've got this isolated Earth orange system out in deep space. Okay? Okay. Therefore, if the linear momentum, y component, in the initial situation is 0, it's got to be 0 always. Even if later the 2 subparts are moving. Because once I let go, release from rest, I know what's going to happen. The orange is going to accelerate this way, towards the center of the Earth. That means it's going to have a velocity as I float out in space observing it. Therefore, it's going to have a momentum. Therefore, the Earth has to have momentum too. And the total of those 2 momentum vectors must be 0. So the Earth has to be moving too, has to be moving that way. Let's see how fast the Earth goes by forcing the total momentum to be 0. So in this final picture, let's write down expressions for the momentum of each of the parts. Okay, for the orange and for the Earth. Oh, let's do the Earth first. Well, momentum for anything is mass times velocity. So for the Earth, that'd be capital M, V, E for Earth. Okay? So that's what this V here would be, VE for Earth. And that's in the plus Y direction according to my axis that I chose. And I want to be consistent with what I chose. Now the orange is moving in the negative Y direction. So I'm going to insert a negative sign to account for direction. And the momentum will be little m for the orange And then that V orange is really technically its speed, because I've accounted for the direction of motion with that negative sign. So there's my accounting for the momentum of both the Earth and the orange, but the total must be 0. Let's use that constraint to solve for the velocity of Earth. Not hard to just solve this equation for the velocity of the Earth. You get the mass of the orange times the speed of the orange over the mass of the Earth. So if I let this arrow here represent V orange, and that other arrow represent V Earth, let's compare V Earth to V orange. How will I do that? I'll use this expression right down here I just derived based on conservation of linear momentum. I'm going to do a little grouping here. What I've just written tells me to think of the velocity of the Earth as being calculated as follows. Take whatever the velocity of the orange is as it's free falling and multiply that by this fraction. This fraction is the mass of the orange divided by the mass of the Earth. I will just tell you that the mass of the Earth is 5.98 times 10 to the 24 kilograms. 5.98 times 10 to the 24 kilograms. What's the mass of an orange? Less than 1 kilogram, but for round numbers, say it's 1 kilogram. Then the velocity of the Earth is, at any given moment, the velocity of the orange times 1 over 5.98 times 10 to the 24. That means the velocity of the Earth is absolutely minuscule compared to the velocity of the orange. And so the scale of these two arrows that I've drawn, VE versus VO, not even remotely realistic. The arrow for VE is so short that I can't really even draw it. Okay? Yet still, because of its big mass, even with a tiny VE, the momentum of the Earth is exactly equal and opposite to the momentum of the orange, and the total momentum is 0. So that's what happens out in deep space when you start with an orange and an Earth initially at rest and you release. The orange accelerates down with a growing velocity VO. The Earth technically accelerates up, but with an absolutely minuscule velocity VE. But the total momentum stays 0. Now, that's not really a Wiley Plus problem. I'm just honing us to practice with the whole concept of determining when a system's linear momentum is conserved. Okay? Now I want you to practice more with that. So here comes a class engagement exercise that you'll answer on Blackboard as typical. Okay? So this next set of questions, sorry, let me bring that down just a little bit so you can see everything, is class engagement on Blackboard. And here's the scenario. We are looking down from above on a two-dimensional XY coordinate system, and we have 3 particles. Turns out they're boxes of chocolates, right? Okay, there are 3 particles, they're drawn in A, B, and C. And for each case, we're shown free body diagrams. At least for the forces in the XY plane, that's all we have to worry about. Overhead views there, okay? So we have these horizontal forces. And you can see by the arrows what directions the forces are in, and they're labeled in newtons their magnitudes. All right, here's our task. For each box, so for A and B and C, one by one, you are to tell me, is the linear momentum conserved along the x-axis? In other words, you are to tell me if capital P sub x is equal to a constant value for that box. And then separately, you are to tell me if the linear momentum is conserved along the x-axis. Is capital P sub y equal to a constant. So for each box, A, B, and C, there are two answers you have to give. You have to tell me if P sub x is equal to a constant, and then tell me if P sub y is equal to a constant. Okay? That's your class engagement exercise. Then you paste it down. Here we go. One more thing to talk about. I want to go into Chapter 9, Section 6, and talk about momentum and kinetic energy in collisions. Remember we talked about collisions when we introduced the impulse linear momentum theorem, and we said we were going to look at collisions quite a bit in this chapter. And that's really actually the rest of this chapter now. We're going to be focusing on the situation in physics where two or more objects undergo what we call in physics a collision. Often, what we're talking about is a scenario exactly like you would think a collision to be. Two things, bang, into each other, for one reason or another, however that happens. Okay? But there'll be a little bit of a generalization. Remember in the previous video, I called a collision the interaction between a box and a spring. I'm still called that a collision. Or I could have an object just sitting, completely minding its own business at rest, and all of a sudden, because of some internal situation, it explodes into fragments, and the fragments go flying off. I'm going to call that a collision as well. Okay, the rest of this chapter is about what a physicist would call collisions. And the key things physical quantities we have to keep track of in a collision are linear momentum and kinetic energy. And I want to talk about those things now. And it turns out to be very convenient when you talk about collisions to take every collision and put them into one of two categories. Only two categories, at least there's only two. They are called inelastic collisions and elastic collisions. Okay? Every collision we consider goes into one of two categories, one of two buckets. It's either inelastic or elastic. Okay? All right, now, here's an important thing to note for us, for the rest of this chapter, and really pretty much the rest of this course. Anytime we have a collision, for all collisions, the linear momentum of the system is conserved. And the system, we mean the things that collide. The system consists of the colliding objects. Now, it is valid for you to want to pause and think about that a little bit. I talked about how to recognize when linear momentum of a system is conserved, and I said I want you to be able to answer the question. What's the condition for the linear momentum of a system to be conserved? And when I ask that, I want you to say, the net external force on the system equals 0. So apparently I'm saying that must be true in the collisions we're going to study. Because I'm saying linear momentum is conserved if the system is the colliding objects. So we will take that always to be true. We have a collision. We take the system to be the things that are colliding. The net external force on that system must equal 0. We will take that to be true. Either because it is exactly true, such as objects sliding around on a horizontal frictionless surface like on an air table or an ice rink. Okay? Or, well, it's approximately true, but we're going to take it to be true. That might be when two cars collide on a roadway. It's not always a frictionless surface, a roadway. There, what the argument is things like that are so short in duration. The delta t is so short that whatever external force there is acting, like a frictional force, doesn't have enough time to change the linear momentum by much, and therefore we don't worry about it. So bottom line, even though it can get a bit subtle when you start thinking about all the details, I am telling you something you can just take to the bank. In this chapter, for all collisions, the linear momentum of the system is conserved, assuming you take the system to be all the things involved in the collision. All right, so that's a given. Put that aside now, all right? The total linear momentum will be conserved in all collisions. Now I'm going to turn to looking at the total kinetic energy of the system. Okay? What's happening to that during a collision? That's where we come up with the two categories of collision, elastic and inelastic. First, elastic. An elastic collision means the system neither gains kinetic energy from nor loses kinetic energy to other forms of energy. In other words, the total kinetic energy the system had before the collision is equal to the total kinetic energy it had after the collision. This is kind of rare. There can't be anything happening that's taking some of that kinetic energy away and converting it into other forms. All right? So, a collision between automobiles on a road, not elastic, because there the objects get deformed, yes? When you have collisions where the objects get deformed, like two cars, or two balls of clay that you throw at each other, and when they collide, they get deformed. Whenever the things get deformed in the collision, it's not elastic. And you're using some of that initial kinetic energy to do work to deform the bodies. And you don't get that back as kinetic energy again afterwards. That's why it's not elastic. If there's any kind of deforming of the bodies, that uses up some of the kinetic energy. Okay? Then it's not elastic. Or that example I gave a moment ago of an object just sitting by itself that explodes into fragments, that is definitely not elastic. You have no kinetic energy initially, and then all of a sudden you've got these fragments moving. You have lots of kinetic energy. You've gained kinetic energy. In that case, in a crash, you lose kinetic energy, like cars. In an explosion, you gain kinetic energy. It must come from, say, chemical potential energy that was stored initially. So I'm giving you examples of things that make it not elastic. So to be elastic, there must be no kind of phenomenon that's converting the kinetic energy into something else or giving me kinetic energy. The total kinetic energy before the collision must equal the total kinetic energy after. So what you have to have are things that are colliding and not deforming in any permanent way. The examples that you often have are, at least approximately, are pool balls, because they're pretty rigid, and they clack off each other, but they don't get deformed in any permanent way. Another approximate version of an elastic collision is the so-called Newton's cradle. The spherical, the steel spheres hanging vertically on strings, and you pull one out, you release, and it hits, and the one on the end goes out. Okay? Those are approximately elastic collisions because those spheres don't get deformed. Technically, you take away some of the kinetic energy to make sound energy, and they do get a little bit warmer, so you take away some of the kinetic energy to make thermal energy, but it's nothing like a collision between two cars or anything. So just in case you haven't seen a Newton's cradle, I'm going to show you a YouTube video. There's, before I run it, you've probably seen this thing. And you just pull one out and you let it go and you let it hit the one, let it hit its neighbors, and then the one on the end goes flying out, right? That's approximately an elastic collision. It's clearly not exactly elastic. Then you can play around with it. You can take two of them out. So two going in, two going out. Or what are they going to do next? How about three? Three in, three go out. Okay, so that's just one example of a situation in which you have a collision. So you must conserve linear momentum. Remember, that's always going to be true in a collision for us. And since those bodies aren't doing any kind of permanent deformation and taking any of our kinetic energy away, you have conservation of kinetic energy as well. So that's called an elastic collision. How will you know if a collision is elastic when you're solving a homework problem? It will have to tell you, because they're kind of rare, as I said. Most collisions fall into this second category, an inelastic collision. Well, that's any collision in which the total kinetic energy of the system changes as a result of the collision, like two cars colliding. I told you this chapter, the rest of this chapter is kind of violent. We talk about things like two cars colliding. Well, they get deformed. That deforming takes work that uses up some of the kinetic energy. You lose kinetic energy. Or an explosion, you gain kinetic energy. Either way, it's an inelastic collision. So what is conserved? Linear momentum, but nothing else. Okay? Now, heads up, under that inelastic collision category, there is a special case that happens frequently enough that we need to note it. It's called a completely inelastic collision. It is the most inelastic kind of inelastic collision there is. So it's a special kind of inelastic collision in which the objects stick together after colliding and move as one blob. That's said to be a completely inelastic collision. You can't get more inelastic than that. And so what I have here is a depiction of a completely inelastic collision in a series of snapshots. We're looking down from above on an XY coordinate system. This is some kind of horizontal frictionless surface, maybe an air table or an ice rink. And initially what's happening is I have particle 1 moving with a velocity v1 initial, happens to be in the plus x direction. Particle 2 is sitting initially at rest. And I'm going to take our system to be the two particles, because they're going to collide. Okay? All right. The system has some center of mass, which will be on the line between them. It's marked there with a very small red X, and that center of mass has some velocity, which is marked with the red arrow and labeled VCOM. So that's the first freeze frame, or the first snapshot. A little bit later, we're right here. Still, particle 1's closer to particle 2. Particle 2 is still at rest. The center of mass has moved a little bit, but the center of mass velocity, the red arrow, hasn't changed. Next freeze frame. They're getting closer. Next freeze frame. Bang! They collide. And this is going to be a completely inelastic collision. Maybe there's something sticky. So afterwards, they're drawn as one blob. Okay? One blob. And we don't lose any mass. So the total mass is m1 plus m2. And then they move as one blob afterwards with a velocity capital V. That also has to equal the velocity of the center of mass, because there's just one thing now moving. I'm going to apply conservation. Well, first I'm going to write down a formula for the velocity of the center of mass before the collision. I want to write that an expression for that first. VCOM initial. Now here I need to just remember a handy little formula that I've used in a previous video lecture. If I've got a system of some particles, 2 in this case, they've each got some mass, they've each got some velocity. How do I calculate the velocity of that special point called the center of mass? Easy. Take the mass times the velocity for particle 1 plus the mass times the velocity for particle 2 and divide by the total mass if it's a 2-particle system. So m1 times v1 initial plus m2 times v2 initial. Oh, but v2 initial is 0. All divided by the total mass. m1 plus m2. So VCOM initial is m1 times v1 initial over m1 plus m2. And if I wanted to, I could give you numbers and you could plug in. But I just want symbols. So that's the symbolic expression for the velocity of the center of mass, and that's true anytime before the collision. Then the collision happens. Now remember what's going to be the correct physics principle to analyze the collision. Conservation of linear momentum. So now I'm going to apply conservation of linear momentum. The total momentum, the total x momentum before the collision, px initial, must equal the total x momentum after the collision, px final. All right, and remember, momentum is mass times velocity for each particle. So for initially, I've got mass of 1 times v1 initial, that's the momentum of particle 1 initial, plus the mass of 2 times v2 initial, but that's 0. So that's the initial momentum, symbolically. So that must equal, now I'm going to write a symbolic expression for the final momentum. Remember, this is a special case, completely inelastic. The objects have stuck together afterwards and are moving as one blob. So I have one particle, but its total mass is m1 plus m2. Don't worry about a particle and you think, oh my God, some piece. Oh, sorry. We will decline that. Don't worry about some piece flying off or anything. If things like that are happening, we will tell you. So just m1 plus m2, total mass is still there. It's just now one blob. And that one blob has some velocity afterwards that this picture labels big V. So I'm going to label that as the final velocity of the blob after the collision. And that's the symbolic expression for the final momentum. Initial momentum must equal final. Let's solve for that final velocity of the blob after the collision. Just do the algebra. m1 times v1 initial over m1 plus m2. Does that look familiar? Didn't I just get that same expression for the velocity of the center of mass before the collision? Well, that's also the velocity that the two things have afterwards to conserve linear momentum. Let's do one more thing, just to make sure it's all adding up. Let's calculate the velocity of the center of mass after the collision. Using the same kinematic thinking that I did before, that I applied to before the collision. So VCOM final. Take the mass of particle 1 times its velocity plus the mass of particle 2 times its velocity over the total mass. So m1, V, big V, right? Plus m2, same big V, over m1 plus m2. Well, then let's factor the big V. So we have m1 plus m2 all times big V upstairs, and m1 plus m2 downstairs, and m1 plus m2 cancels, and VCOM after the collision is just that common velocity capital V that they have afterwards from conservation of linear momentum. So, the center of mass moves along at constant velocity even after the collision. The collision does not change the velocity of the center of mass because linear momentum is conserved in the collision, and that's what keeps the center of mass velocity constant. That's just a little bit of practice, just getting warmed up. So we're going to be doing examples in class, and you're going to be doing homework problems where we apply conservation of linear momentum to inelastic collisions. And in the next video lecture, we'll talk more about elastic collisions. But that's all for this video.